Good morning, everyone. We will quickly revise the previous lecture before we go on to the fourth case of decision trees. We said that we are using decision trees because they are very simple models, they are very interpretable, and the rationale we gave was that let's compare the interpretability of our model with respect to something like a neural network, where the model is learning a huge set of numbers encoded as the edges of this graph that you see, right? In comparison, what we said is that a decision tree might learn something like this, which we believe is very interpretable. Any decision that you want to take is just walking down the tree. We said that the core idea of the algorithm of decision trees is using greedy approximations, is using greedy algorithm. In greedy algorithms, the design is that we take a decision which looks best at that particular moment. It may not be the best decision globally. What do you think is so in the decision tree algorithm that we looked at last time, what was the greedy decision that we had taken? We took the decision as to which attribute we should be choosing, only looking at that particular level, right? We did not look at, let's say, what will be the best attribute two rows down, two depth further down in the tree, right? We just looked at the best attribute at that particular moment. This is the reason why it's a greedy algorithm. We looked at this particular data set containing 14 examples of whether one should or not play tennis. We said that we need to choose an attribute which gives us the most clarity once we have chosen that attribute in the tree. So we said that we want something which gives us the best estimated performance gain. To get best estimated performance gain, we first need to get a sense of what is the level of confusion or the level of entropy. So thus we use entropy as a means to characterize the impurity of examples of the confusion. We said that if the probability of plus is 0 or 1, we have no confusion. All of the examples can trivially be told to be either 0 or 1 or true or false. There is maximum confusion when roughly half of the samples are positive class and roughly half are negative, in which case in a binary classification problem the entropy is 1. We said that we can then use information gain as a criteria to choose which attribute we should be looking at. So we looked at this particular formula, gain of set of examples S and an attribute A. We said this is you first find out the entropy of the set of examples S, and then you consider the weighted entropy of the subsets once you have divided the set of examples via the attribute. So we took this particular example. We said that the entropy of this set is, we have 9 yeses and 5 nos. So the entropy is via this formula, it comes out to be 0.94. We wanted to calculate the information gain for outlook attribute. We said that on outlook we can take 3 different values, sunny, overcast and rain. So we divide our data set into 3 subsets. For each of these subsets we calculate the entropy and we calculate the weighted entropy. We note that for outlook equal to overcast we always play. So there is no confusion, the entropy is 0. And then we find out the information gain for the set of examples S using outlook as the attribute. It came out to be 0.246. We repeated this exercise for all of the attributes and we said that at this level of the tree the best attribute looks to be outlook. So our tree at this stage looked like outlook and then the 3 branches corresponding to 3 values which outlook takes, followed by, now we call the same procedure on the subset of the tree where outlook takes sunny and outlook takes rain. After this stage we got the tree which finally looked like this. We said that to make a prediction in the tree we just need to walk down the tree. For example, for humidity high, strong wind, sunny outlook, hot temperature, we first look at the outlook. In the example we want to predict, the outlook is sunny, so we walk down this path, outlook is sunny. Humidity is high, so outlook sunny, humidity high, we make the prediction no, we don't play. We took the second category of decision trees where the input was discrete but the output was real. So this corresponds to a regression like setting, and almost everything in this algorithm was the same, but the measure of impurity changed. What is the measure of impurity we used here? The variance, mean squared error, something like that, right? So we used mean squared error, and similar to information gain, we used the reduction in MSE as a criterion. So for wind attribute, the mean squared error on the set of examples S before we had done the split was 311. Once we did the split, we create two separate data sets, wind is weak and wind is strong, and for these we find out the weighted MSEs, which is weighing by the number of examples. Once we did this, we found out that wind is the most important attribute for this data set at this stage, and then the tree looked like this stage. The third case which we took was real input, discrete output. Is this classification or regression? Classification, because the problem definition is decided by the type of output. It's discrete, so the classification problem. Now we can't trivially divide the data set because it's the input features, the attributes, because they are now on a continuous scale. You can't really say that temperature equal to 40 or temperature equal to 48. So you can't really put, if you were to use this data set and choose the values to split on, like we did for the discrete case, we'll have 6 different values, right? What accuracy will we get, or what accuracy will we get for such a tree on the train set? 100%, right? You have memorized the data set. You have not done any intelligence here. All you're saying is that your tree would look like temperature is 40, play tennis, no. Temperature is 48, play tennis, no. Temperature is 60, play tennis, yes, so on and so forth. So that amounts to just memorizing the data set. You have not done any learning as such. So therefore, we need to get a smart way of finding out the splits when the input attributes are continuous. One way to do that is you sort by the input attribute in increasing order. In this case, we have 40, 48, 60, 72, 80, 90, and between consecutive pairs, 40 and 48, 48 and 60, we choose them as possible attributes possible values where we do the split. So once a split could have been temperature greater than 44 and less than 44, another could be temperature less than 54 and greater than 54, and so on and so forth. We're still making binary decisions only. So in this case, we're looking at binary splits only. And we looked at a specific example in which we were looking at two input features, x1 and x2, both being real, and the output is discrete. It's a class that we're trying to predict amongst the 4 classes here: red, purple, yellow, and blue. Depth 1 tree is very trivial. We don't get a very good classification. Depth 2 tree, you see that we are subdividing the space into smaller subspaces. Depth 3 tree looks like a very good fit at this point. If we keep going further, you will notice that we will keep getting each and every point accurately at one stage. Right. So now the tree is highly specialized. It's able to get each and every point, almost each and every point correctly. And in order to do that, it created these various complicated structures. Like it created a red region here, it created a small purple region here, which looks a little out of place. Any questions on this? This is where we stopped last time. Okay. So, couple of logistical announcements. One, some of the TAs might have reached to a subset of the students where either the prerequisite test was having you submitted the wrong link, or you had not sufficiently solved the test. So, we have reached out to you. Please reply back with all the edits, with solving more questions if needed, or if you have given the wrong link, please give us the right link. If there's still someone who has not submitted the prerequisite test, please do that. Otherwise, you may be told to drop the course. The other thing, please, the people in the first desk, you can please roll out a A4 sheet or any sheet for attendance purposes. And next time onwards, please do come on time. It's now 8:42. The class starts at 8:30. It not only disturbs you, it unfortunately disturbs the other people who are there on time. So please don't force my hand by, if this continues, I may have to just close the door at a certain point, in which case you lose the attendance, you lose the lecture. So if you are anyway making the effort to come at 8:40, please make slightly more effort, please come at 8:30. Sorry? So microphone not working. Are the people at the back able to hear me? Can you ask them to give me a new cell? I think the battery has died. Yes, the battery has died. In the meantime, I'll just speak a little louder. Okay, real input, real output. Is this classification? Is this regression? Regression, right? So an example of this might be a data set like this, where the input is on the x-axis, while it's an integer, but think of this as a continuous value, and y-axis is showing the y value. So if you were to fit a decision tree on this, how might the prediction look like? Can you work this out in your notebooks? Think of what it might do. Think of decision tree of depth 0, decision tree of depth 1, and decision tree of depth 2. I want you to think of these answers without working out any maths. So that will help you understand the concepts better than just working out by using information gain or any such criteria. You have to make the predictions on all the set of points between 1 and 6 using decision trees of various depths. It's a regression problem, not a classification problem. So your output y could also be any number. In this case, it will have to be some number between 0 and 2. For each x, the output will be some number between 0 and 2. So draw a decision tree of depth 0, depth 1, depth 2. And while we're getting the biometrics sorted out, I'll also randomly call out 5 or 10 people from the roll call. So don't play mischief. Okay, what does the depth 0 tree look like? So depth 0 tree means what is your prediction even without looking at the input. Call Dharmesh.
Yeah, the phone was inside, so I found the cleaning supervisor. He either got someone else.
Okay.
So that audio vision person is
So
coming.
we just need a pattern. Yeah, so depth 0 tree means that you have not looked at the input variable at all. You just want to make a prediction, which is basically now a dummy regressor. So a dummy regressor which best predicts the points where y is 0, 1 and 2 should be y equal to 1. It's a constant line which will best represent all of these data, which gives you a hint as to how the tree might be built further for this case. You're trying to divide the data into by the input variable of concern, and a prediction within that specific region is the mean of the y values, right? So if you have not done any division on the input features, our prediction is the mean of all the y values, which is a good enough estimate. So this is how the decision tree of depth 0 might look like. It makes a prediction of constant 1. Right? Now decision of tree of depth 1 will make one split. Right? Now that split has to be made on the x feature, which is having values 1, 2, 3, 4, 5, 6. Right? What all could be some battery? What all could be some potential regions, places to split? Would x equal to minus 50 be a good split? No. Why? Because all of the points are to the right hand side of x equal to minus 50. Would x equal to plus 8 be a good fit, a good point to split? No. All of the points are to the left of x equal to 8. How about x equal to 3? or x equal to 2.5. Would that be a good point? Why? Because at x equal to 2.5, you see that there are 2 points to the left of it, both of which show 0 variance, right? Both of which are at y equal to 0, and to the right of it you have 4 points, 2 of which have a value of 1 and 2 of which have a value of 2. So, the decision tree of depth 1 turns out to be something like this. For x less than 2.5, the y values that you have seen in the training data are 0 and 0, the mean of which is 0, and on the right hand side you see that the y values that you are getting are 1, 1 and 2, 2. What is the mean of these 4 values? 1, 1, 2, 2, 1.5, and that is our prediction also for the points where x is greater than 2.5, right. So, that is the basic algorithm. We will be splitting on an input attribute x equal to some constant, x less than some constant and x greater than equal to some constant, and for values which are below, so in this region we will take the mean of all the y values, and similarly we will take the mean of all the y values in the other region. Any doubt, question in this? I have still not formally defined it, I am just giving the intuition behind this. So, this is how scikit-learn will give you a decision tree representation at this, for this tree that we have just seen. It is showing me that the split was made at x less than equal to 2.5, which corresponds to what we have seen earlier. The number of samples before we have done the split is 6. Right. Does that make sense? We have 6 samples overall. The value is 1.0. So, if we had not gone further down in the tree, what is the value that we would have predicted? 1.0, which is the mean of all these 6 points. Right. The mean squared error, the squared error is 0.667. Right. So, this is coming in from the fact that you take the mean of all these points, mean of 0, 0, 1, 1, 2, 2. What is the mean of all these points? So, 0 plus 0 plus 1 plus 1 plus 2 plus 2 divided by 6. So, 2 plus 2 is 4 plus 2 is 6, the mean is 1, right. So, you calculate the mean squared error or the squared error with respect to that, and you get 0.667, and then you say that let us now see that if we had divided our data set based on this particular attribute less than equal to threshold, true and false, x less than 2.5, how many points do we see? 2, and x greater than 2.5 we see 4 points. So, this is what the tree is indicating. The squared error on the region where x is less than equal to 2.5 is 0. Why? Because all of the values are 0, the mean is same as all the values. So, the squared error is 0, the number of samples is 2, the value is 0. So, the prediction made from this part of the tree is 0, because that is the mean of all the points in this region. What would be the number of samples in the right hand side region? 4. What would be the mean squared error or the squared error? Usually the mean square. What is the mean of these 4 points? 1.5. You do 1.5 minus 1 square plus 1.5 minus 1 square plus 2 minus 1.5 square plus 2 minus 1.5 square divided by 4. What should you be getting? 0.25. Number of samples is 4. The value being predicted is 1.5, which is the mean of all these points. Okay. Yes, so that we will come to in a second as to how we decide which point to split on. That will come to in a second. But does the tree make sense once we have made this decision? Does the tree look okay to you? Interpretable? Okay.
Is it like we are creating depth 0 tree again after splitting?
We are creating a depth 0. You can think of it this way, yeah. You are creating a depth 0 tree again. So, it is an iterative procedure, it is a recursive procedure. You can think of that way also. Okay, how would a decision tree of depth 2 look like? Can you draw that? Would you need any split on the region less than 2.5? No. Why? Because the mean squared error is 0. On the right hand side, the mean squared error is non-zero. You can still do a split and get something better. Where would you make a split? 4.5? Does this look like what you would have made? Right. The next split you make it as is 4.5, and the decision tree would look like this. So x less than equal to 2.5 is what you'd seen. If it is false, it means x is greater than 2.5. Then the squared error you saw was 0.25, the number of samples you saw was 4, and the value which was predicted was 1.5, but we can do a further split. That split comes at 4.5, and for 4.5, so now we are looking at this region. X is greater than 2.5 and x is less than 4.5. So it's this region I am highlighting with the mouse. What is the y value that you will predict? 1. What is the squared error? You will have 0. What is the number of samples? 2. And that is what you will see. Squared error is 0, samples is 2, value is 1. And for the last region, so this is x greater than 2.5 and x greater than 4.5. The number of samples is 2, the mean is 2, the squared error is 0. And therefore, this is the tree that you will get. Right? Questions on this? Okay. What would be my prediction for x equal to 10? 2, right? Do you see that you will always keep on predicting the value which you saw at the last most training point? Right? What is the prediction at x equal to minus 20? 0. Right? So, you will continue making that prediction. You are not learning any linear like trend. Right? You are not learning a line, you are not learning any polynomial feature, you are just learning something which is fitted well on the data that you have seen, and extrapolation performance would be just giving you the last value that you have seen. Okay, let us see how to make this split. Where should we make that split? We made it at 2.5 and 4.5. We have already shown you that making split at minus 20 or making split at plus 80 don't make sense. Right? So, what we are saying is that we perhaps have to make the splits between the data points that we have. Now, how do we optimally do that? We will say that let our feature be x, the label be y. The split would be something like x equal to s, or x less than equal to s and x greater than s are the two boundaries, are the two regions that we get. So, let us call these two regions as R1 and R2. R1 is x less than s and R2 is x greater than equal to s, or so you can be a little careful about the less than equal to and greater than equal to. So, in this case we had chosen s equal to 2.5, region 1 was this region where my mouse currently is, and region 2 is this region of x greater than equal to 2.5. Right. So, I have broken down my overall region R into R1 and R2. Now, we take C1 to be the mean of all the y values in R1 and C2 to be the mean of all the values in R2. We did this here. So, if we had chosen x equal to 2.5 as a split, we look at all the y values in R1, take the mean which is 0, and we look at all the y values in R2, take the mean which is 1.5. So, for this split we will have C1 equal to 0, C2 equal to 1.5, right. For split x equal to 2.5 we will get this regions. Now, you are trying to minimize this particular quantity which is yi minus C1 given xi belongs to region 1 square plus yi minus C2 given xi given R2. So, this looks like a very complicated term. Essentially what this is saying is, once you found out C1 and C2 in a particular region, right, you found out this R1 region, R2 region, you found out C1 to be 0.0, you found C2 to be 1.5. Now, you look at all the points in R1 and you find out the squared error with respect to the mean, right, or you just find out the mean squared error. Similarly, you find out the mean squared error for region 2, right, and you are adding those up. And then you are just adding those mean squared errors. So, for this particular split that we had chosen, the mean squared error for the region R1 is 0, the mean squared error for the region R2 is 0.25, right. So, the overall mean squared error that we are getting is 0.25. Now, if you had chosen a different split, let us assume that you had gone overboard, you had chosen a split of x equal to 0, right. What is R1? You do not have any point there, right. So, let us not confuse that way. Okay, so, let us just choose x equal to, let us say 1.5, right. So, C1 contains only one point whose mean is 1, the mean squared error is 0. What is the mean squared error for R2? You have 1, 0, you have 2 1s and you have 2 2s. What is the mean of 0? 1, 1 and 2 and 2. So, it is 2 and 2, 4 plus 1, 5 plus 1, 6 divided by 5. The mean is 1.2 and you will find out the mean squared error. So, 1.2 minus 0 square plus 1.2 minus 1 square plus 1.2 minus 1 square plus 1.2 minus 2 square plus 1.2 minus 2 squared, and then you will take the mean over by dividing this quantity by 5. This entire quantity will come out to be greater than 0.25, right. You can verify this, which means that the split at 2.5 is better than the split at 1.5, right. So, now does this give you a hint as to how you may be deciding where to split on? So, sort by that particular attribute, look at any two adjacent points and choose the midpoint as a potential split. So, the potential splits here are 1.5, 2.5, 3.5, 4.5, 5.5, that is it, right. You enumerate all the potential splits, you calculate the sum of mean squared errors across the region R1 and R2, and then you choose which of them gives you the lowest possible values, right. So, here you are searching over a certain number of discrete possibilities, you are not searching in one way in a continuous space. You only have a few finite possibilities that you want to check. If you had split at 4.5, you would have got similar results, and sometimes it is just random. Like if you get the same objective, if you get the same information gain, this happens in the other tree variants also, then you can choose randomly which of them to pick. The user has to take the decision, or it is typically a random decision. You toss a coin and you decide between the different possibilities.
So, are there not any other factors that affect this choosing of splitting point?
Are there any other factors which affect the splitting of this point? Can you elaborate? Like what kind of factors are we looking at?
Like you said that if mean square error is same, we can choose any randomly choose any point. So, are there not any other factors?
Okay, so the question is, if the mean squared error is the same for two particular splits, how do you choose? I think it is generally broken randomly. So, such ties, so you will hear this term a lot in machine learning, ties are broken randomly. In certain cases, they may choose the first one. So, it depends on how this person who has implemented is written. Other questions? And we just discussed the algorithm that we will follow. We sort all the data points in increasing order of x. We evaluate the loss functions for all the split points which are between two adjacent points and select the S with the minimum objective. How will we do the same exercise if you have more than one attribute? Here I had shown you just one attribute x. If you had x1 and x2, what would you do? Okay, good. So, if you have multiple attributes, you will repeat the same procedure across the different attributes. So, now you are not just picking up the best split point, you are choosing the best pair of attribute comma split points, or for each attribute you pick up the best split points. So, you will have attribute A1 comma split point S1, A2 comma S2, so on and so forth, and then you pick up the one which is the best amongst these. At each stage of the decision tree, you can make this distinction. Now, in the case of discrete output, I had mentioned this particular line, recursive call, ID3 on examples we target attribute minus A, right. Once we had seen a particular attribute in the first case of decision tree, we don't need to see it again, right. But we don't do it, but we don't remove the attribute in this particular case, which is real input, real output. Why? Do you see the question? So in this case, in this tree, once I'd seen outlook, there is no benefit of having outlook as a node further down in the tree. But in the new case that I am showing you, real input, real output, I have already shown you trees which are multiple times splitting on the same attribute. So why this distinction? Why is this okay? Yes.
Because here we are operating on real numbers and they are infinite. So even between two real numbers, there will be infinite there.
Yeah, you're working in a continuous space, and here we can very clearly see as a simple example that we can do multiple splits and keep getting a better estimate. Okay, any question on this? Okay, let's try and work this out in this notebook. Again, now we don't need to solve any maths. I just want you to imagine that you're given this data set y equal to sine of x with x varying from 0 to 7 with 10,000 points. So data set might look like this. Can you draw a decision tree of depth 0, 1, 2, 3 without working out any maths? Let's see how you're able to capture the intuition behind how the sign behaves and how decision trees work. You may want to go beyond 0 and beyond 7 also in your prediction. So let's say you want to predict from minus 0.5 to 7.5. Can I request the people with the laptop to please turn off their laptops? It's mentioned in the FAQ, no laptop policy, please. Okay, how does the decision tree of depth 0 look like for this data? It has to be a straight line passing through 0. Okay, I'm starting with, in this case, I'm starting with decision tree depth 1. Does the split have any physical significance? 3.14 pi. So this is a decision tree of depth 1, a decision tree of depth where I'm not controlling for any depth looks like this. Why does this have this weird shape? Why does it not uniformly chunk up and break the input space? We see that this particular rectangle or this particular region is quite big compared to this particular rectangle. Why? Because of the slope or the gradient. So y changes very slowly over here, right? So therefore, any reasonable value, so any value which would suffice for a long time because y is not changing much, but y changes quite rapidly at the beginning. Right? If you want to go down the rabbit hole, you can also say that the gradient of sine is cosine and the cosine of smaller values is close to 1. So therefore, you see much more changes in y when x is small. Right? Therefore, you need to, so single value of y will not suffice for a longer region. Right? Therefore, you end up creating a structure like this, a prediction like this. And as discussed, beyond the last point that you have seen, your prediction will just be a constant on both sides. Will this be a good fit for predicting the sine function beyond 6.5? No, right? It will just give you a straight line. So these are some things you have to inherently think about when you are solving machine learning problems. If only given this amount of data, you may think that your model has done very good, right? But it's actually done very bad, and because it's not got any generalization capability. But if you at the background had some knowledge that the data that you're trying to fit is some kind of a sinusoidal signal, you could have just learned 3 parameters, let's say 3 or 4 parameters. One is the frequency of the signal, one is the phase of the signal, and you would have got a much better result than this decision tree of depth infinity that you've learned. So with this, we'll just summarize what we've learned in decision trees. This was the first machine learning algorithm that we've looked at. We started off the discussion with saying that interpretability is an important goal. There are much more sophisticated algorithms which are harder to interpret. Decision trees are very well known interpretable models. We also said that learning an optimal tree is hard. So given any number of attributes, you can come up with so many combinations of attributes which you could have chosen, a lot of trees that you could have chosen based on the number of attributes. But instead, we choose a simple algorithm called greedy algorithm, which makes an approximation that at this stage, what is the best attribute to choose. We want to recursively split the input data into maximize the performance gain. The definition of performance gain varies as per the problem statement of interest. We are looking at entropy and information gain, and in the continuous variable outputs, we are looking at the mean squared error and the reduction in mean squared error. One such problem is that they can overfit very easily. We have not yet looked at the definition of what overfit means. And the second issue is that empirically they are not as powerful as many of the other methods, like random forest or neural networks or support vector machines, etc. But they're a good first algorithm to study. Any questions in decision trees?
The last example, how will the depth 2 tree?
So depth 1 tree is like this. Depth 2 tree will say that now let's look at this region, and now let's look at this region. Both of them are done separately. In this region, where should you make a split? Again, you'll have to choose based on the criteria that we have, mean squared error, and eventually you'll see that there will be larger regions spanned over here and smaller regions spanned over here. Good exercise to try out on your own. The code is already available. I will just link it up after the class. You can run it here. Other questions? Okay. Okay, now we are going to solve this important problem, that what should be the depth of the tree so that we get good performance. Right? I've purposefully kept some of these terms vague as to good performance and what do you mean by performance, what do you mean by good. How do you specify these things? We'll see this in the current set of slides. We're looking at the decision tree classifier, which means we have two classes, purple and yellow. What do you think would be the decision boundary of a decision tree classifier? If it's depth 1, does this look like a reasonable split to you? Right? You may also see that I have, in this particular tree that I am showing, you can see that instead of entropy, there is something else written as Gini. So it's yet another criterion that you can use instead of entropy to understand the measure of entropy that you have, a measure of uncertainty that you have. And here, x1 less than equal to 4.0, this is a split that you will make. Gini is 0.5, samples are 12, value 6,6. What does 6,6 mean? What do you think? You have 12 points, 6 are class 1, 6 are class 2. Right? So therefore, at this stage, if you were to make any decision, it would be almost random. But once you've made a split, can you see that at this split, in this region, in this region which I'm showing in purple, we have 5 purple points, 1 yellow point, and the other one we have 5 yellow points, 1 purple point. So this seems to be a very good split, and the tree is also showing this specifically. Okay, how would a tree of depth 2 look like for this data? Now you have to split this each of this purple region and the yellow region again into smaller trees. Right? How would it look like? This is a decision tree where I have not kept any depth limit. Right? I let it learn as much as possible, so that each and every sample in the training data is learnt perfectly, it's classified perfectly. Right? So this is such a complicated tree that it's incredibly hard to even see the entire tree. Right? You'll have to squint in order to see. But importantly, you'll see that, so by the way, the nodes which are colored in dark are the leaf nodes. The leaf node is the node where the decision has been made. So this is a leaf node where it says that if x is less than 1.5, value is 6, 0. So you can see that x less than 1.5, all of the values are the purple class. Right? So you get perfect classification, it's a leaf node. x1 less than 1.5 and x1 less than 5.5, and there you can see 6.0. So x1 is greater than 1.5, but x1 is less than 5.5. Greater than 1.5 or less than 5.5. Right. So you can keep going down this tree, and eventually you will see all of the samples have been perfectly classified.
Sir, if we do this, like first if we make a depth 0 tree then a depth 1 tree, in that way the depth 0 split will be different.
The depth 0 split would be a constant value predicted. The algorithm did the split on x equal to 1.5. Okay.
But if we would do it like we just did in the previous case,
Mm-hmm.
we would take x is equal to 3.5.
Mm-hmm.
So we change the depth 0 split.
Yeah.
So is it that when the depth changes, all the splits change?
Okay. Let's see. So first, let me verify that the data set is exactly the same. Okay, this is a small mistake at my end. The data set itself is, I think it should be the same. You are incrementally, because you are recursively calling it on, because that's what it means by making a greedy decision. Once you made the decision, you have committed to it. It's a greedy decision. You can't go back and change the other node. So in this case, actually, it's a small mistake that the data set itself is different. Therefore, you will end up with something looking very complicated. But in essence, the story remains the same, that once you increase the depth of the tree, you can learn much more complex decision boundaries. Right? Your machine learning model has become much more sophisticated. But much more sophistication can sometimes lead to very poor generalization. It depends on, again, how you define generalization. But let's take this data set again. So we had the data set shown on the left as the trained data set, and data set shown on the right to be the test data set. Perhaps these 2 points, purple points that you're seeing, are just outliers or measurement error, something went wrong. What do you think could have been a good decision boundary? By just looking at the test set. We'll never have access to it, but what could have been a good decision boundary? Perhaps a rectangle, right? And the inner rectangle contains yellow points, the outer rectangle contains, everything outside the inner rectangle is purple. That could have been a very good boundary, but let's look at different decision tree depths now. This is a very small decision tree, and you note that it misclassifies a lot of points. Right? So I said that let's just choose depth equal to 2. Right? It's a very, very simple tree. You will see that these particular purple points are wrongly classified even on the training data set, and these particular points are also predicted wrongly on the training data set, right. So, this phenomena where you are not able to get good performance on the training data set is known as underfitting. You have not been able to fit well to the training data itself, right. This is also sometimes known as high bias, because you made a very wrong bias assumption about the complexity of the data. You made certain assumptions which are invalid. Towards the end of the class, we look at yet another interpretation of bias, which is more mathematically involved. But for now, let's call this phenomena as underfitting, when we are not able to even fit well on the training data, or we make some misclassifications or incorrect predictions even on the training data, right. At the other end of the extreme, we have something known as overfitting. Now, overfitting will perform extremely well on the training data. As you can note here, each and every point in the training data you are able to get correct classification. Right. But this leads to a very sophisticated looking decision surface, and perhaps these 2 points in the middle should have not been predicted to be purple, they should have just been predicted to be yellow. Right. So, overfitting is also known as high variance. Now, when you hear the word variance, we mean that small changes in an input will lead to large changes in the output. This is a decision tree of depth 10. Now, I mentioned that small change in the data can lead to very different models, right. Now, this is data set 1, data set 2. The only difference in data set 1 and 2 is that 2 points have been swapped, their classes have been swapped. If I learn a decision tree of depth 0 or 1, do you think that the decision trees would be different, or would they be fairly similar? They will probably be fairly similar. If I learn a decision tree of infinite depth, will they be very similar or very different? They will be very different, which you can see in this diagram. The left hand side tree corresponds to the left hand side data set, and the right hand side tree corresponds to the right hand side data set. And you can very clearly see that the trees are very different in the depth, in the nodes that they have chosen, right. So, what is the message from this slide then? A small perturbation in the training data, if it leads to a large perturbation in the learnt model, and as a consequence a large perturbation in your predictions, it means that your model has overfit or it exhibits high variance. High variance, small amount of change in the input training data set leads to highly varied, very different model, and thus a highly varied prediction set. So, therefore, we use these terms often synonymously. Underfitting, high bias. Your model exhibits high amount of bias or high amount of you have made some bias assumptions. Underfitting, because you have not been able to fit even on the training data well. Thus, you can't be expected to do well on the training, on the test data set or unseen data set. Whereas, for overfitting, you have done extremely well on the training data set, but you do not have the capacity to generalize well, because the model exhibits a high amount of variance, which means even a small perturbation to the input training data set will lead to high amount of variation in the learnt model, and thus high amount of variation in the predictions. Whereas, a good fit might have looked something like this, something in the middle, with some lesser amount of depth. So, typically we draw these curves, which are known as accuracy versus complexity curves. We look at 2 data sets. One is the trained data set, which is made available to you, over which you want to train your model. The second is the test data set. For the purpose of simplicity, we will thus far assume that test data set is some unseen data set, which your model has not seen, but you want to predict on that data set. So, what do you notice from these curves, which have been actually drawn for the particular data which I had shown? What can you infer from these? What happens when the complexity or the depth is less than 4? What can you say about the train accuracy? So, it is not very high when depth is less than 4. So, you can also broadly see that as the depth increases, the training accuracy will improve. Right? As you make the model more complex, you're giving it more degrees of freedom in order to learn everything it has to learn in the training data set. Right? We saw this, right? If I keep depth very low, I exhibit high bias, but I'm not able to learn very well on the training data itself. If I don't control for the depth, or I make the model as complex as possible, I'll get very good accuracy on the train set. Right? As you increase the depth, the accuracy in the train set is bound to improve, at least for an algorithm like decision tree. There are other algorithms where that may or may not always happen. For decision trees, this is bound to always happen. If you want, you can note this question down. I may ask this in some of the future quiz. Why is this behavior expected? As you increase the complexity of the decision tree or increase the depth, you will always get more accuracy on the training data set. Whereas a good fit is something in between. So we said that as the depth increases, the train accuracy will improve, but the test accuracy also improves, but after a certain point it decreases. Right? So you notice that the test accuracy shown in orange improves up to a certain point, but after that it starts reducing. Why do you think this behavior exists? Why should the test accuracy decrease after a certain point? Because of overfitting, which means that you've learned some nuances specific to the training data set, which may or may not exist in the test data set. So therefore, we can divide the region into 3 categories. X-axis is again the depth or the complexity of the model. The first region, where our model is not very complex, is the underfitting region. So underfitting we define only basis the train accuracy or the train error. The train accuracy is not good enough. Right? You have not had sufficient complexity to learn even the training data set. On the other extreme, you have overfitting. Your train accuracy will keep on improving, but the test performance decreases after a point because you've overfitted to the training data set. And something in between is a good fit, which is typically what we aim to find. Questions on this?
So, will the underfitting parameter at the point where change from underfitting to good fit starts for training data set and for the test data set always be same?
Okay, the question is that here we see that the trend between the train and test set is almost similar. Right? They both start improving at depth equal to 4. Is this always the case? No. This is a very trivialized example that I am showing, probably not very representative of the real world problems that you will solve, but I had specifically shown this to make it an end-to-end example. This is using the same data which we had seen earlier. Typically, this may not be happening in practice. Other questions?
So, in that case, what would be the boundary for a good fit? Would it be the change in slope of training data set or test data set?
Okay, good. So Deep asks this question as to how would you find out the region of good fit? That's one of the important problems in machine learning. How do you think we can find out that? He is looking at some heuristics. He's suggesting some heuristics that perhaps we look at the train accuracy curves and we look at the region where there is a slight change in slope, or the region where you get diminishing returns. Does anyone know this term, diminishing returns? Can someone expand on that? Explain what you mean by diminishing returns. Okay, so let's say you want to let's talk about the amount of marks that you get in a particular course. So maybe if you just put 10 hours of effort, you will get 80 marks. If you put 10 more hours of work, will you get 160 marks? No, you will probably get 90 marks. If you put 10 more hours of work, will you get 100 marks? Probably not. You will maybe get 95 marks. You put 10 more hours, you will get 98 marks. 10 more hours, 99 marks, 10 more hours, 99.2 marks, 10 more marks, 10 more hours, 100 marks, right? So, for the same increment in the input hours, you are getting relatively slower and slower gains in performance. That is diminishing returns. Similarly, you can keep increasing the model complexity, but you will get diminishing returns. After a point, the accuracy will more or less saturate. And that's one good way to think about choosing the point of a good fit. But the important thing is that you're only looking at the train performance and you're looking at saturation point. You're not looking at the test performance. Why can't we look at the test performance and decide a good region? Why can't we just say that the test performance is the best at minimum depth 4, just choose that point as your optimal depth? Does that make sense? Can we do that? The test set is never made available to us. So, that's the first thing you should always remember in machine learning experiments. This we are just showing post hoc. The test set is never available to you before you learn, before you start with your experiments. So, we need to find some other mechanism which we will see in few minutes. Other questions? Okay. So, now I look at a different definition of bias and variance. So, I will want all of you to be a little more alert. This is slightly more complicated topic compared to the topics we have looked at thus far, and I will show that over a notebook, not over slides. So, it is useful for you if you want to wake up your friends and become yourself more attentive. Can you see the code clearly, or do you want me to make it slightly bigger? Okay. So, I am showing you a generative process of how a data set might have been created in the real world. I have certain ranges of x. I am generating some data set from 0 to 10 with 50 points in between. I create a ground truth function or the true function which maps from x to y, right. So, perhaps the x is the age of a person, right. The y could be, let us say, the height of a person, and let us say there is a complicated physical world formula which exists, right. If you know all the physics behind the growth or the weight of a human being down to the atom, you can actually come up with a perfect function. Let us assume that this is that perfect function which maps between x and y, but our instruments which measure any quantity of interest are typically never 100% correct. They give you a certain amount of errors. Secondly, we always make some assumptions in a physical model. So, we are never able to get all the possible inputs of interest. Let us say if I want to predict the weight of a person, just knowing the age is not enough. You may need to know their genetic history, you may need to know the amount of running that they do, various kinds of things. You may need to know the let us say the height and the weight of their family members, etc. So, what I am saying is that there is always some amount of unknown which exists, which you are not able to accommodate via any true function that you have mentioned. So, typically in practice we write that the observations, which is y, is the true function plus some noise, right. This noise could come in the terms of observational noise, which means imperfect instrument. This noise could be in terms of variables which you have not been able to account for. So, I plotted this data. This is the true relationship between x and y, and the red points are my observations, right. Now, I can fit various complexity of models. I will first start with the tree, and then for practical purposes I will move on to a different model. You do not need to care about the specifics of the model. On this data set, I am showing you the different trees of various depth being learned. Depth 1 tree, it is as per your expectation, it will make one split, and just so you are trying to learn given the red data points. Do not get confused with the blue curve that you are seeing, that is never made available to you. You are only seeing as inputs to the model the red points. For depth 1 tree, maybe this is the tree. Depth 2 tree, maybe this is the tree that you will get. As you increase the depth of the tree, By the way, this is a regression problem. As you increase the depth of the tree, what do you notice? The fit becomes better up to a point, and can you see that now the decision tree predictions shown in the orange, they are more and more passing through the points, through the red points, right. So, here if you look at depth 1 tree, maybe just a couple of points the orange line is passing through. Depth 3, do you see that specifically it is able to pass through some of the corner points, etc. Depth 4, even more passing through the points. Depth 9, what is happening now? Has the model overfitted? It is now not looking at the patterns which exist in the data, but it is also trying to capture each and every nuance of the training data set which has been given, which is noisy, right. The training data set is noisy, we explicitly added that noise. It's trying to capture each and every point of that, whereas a simpler model, maybe a depth 2 or a depth 3 or a depth 4 tree was a slightly better fit. I'll move on to a different model, which is known as linear regression. We have not yet studied linear regression, but let's assume that you're trying to fit various degree polynomials to this data set. You're trying to fit a 0 degree polynomial, which is y equal to x, y equal to constant line, you're fitting a line, you're fitting a second degree polynomial, and so on. Okay. If you were to fit a degree 0 polynomial, does this look like a good fit? Right. This orange line that you're seeing should be the mean of the y values of all the red points. Right. This is the same as what you'll get with decision tree of depth 0, the same as what you'll get with a polynomial fit of degree 0. With degree 1, you should expect to see a line, and there is some linear relationship in the data. So, you can see that the line will slope downwards. As you increase the depth, you will see that the fit will become increasingly better on the training data set, which is exactly what we saw with the decision tree also. But I now make an important change. Right. Thus far, I have been fitting on the entire training data set given to me, but I could have been given a slightly different training data set also. That is also possible, right. From the universe of all the data sets which could have existed, I have been given one small sample, but I could have been given some other sample as well. Right. If I train my model on some other sample, would you expect me to learn the same model or the different model? That would depend on the complexity of the model, and we will see that. So, this is an important set of lines I want you to look at. I have 50 points. What I am saying is that let me choose a subset of 15 points, 15 points from the 50 points. Right. I will say that let us assume that I had access to some random subset of these 15 out of 50 points for my training purposes. And for each such random subset which I have, I will train a different model. Right. Same model class, but different instance of the model. So, what I will do is I will fit for the given data set, which is a random subset of 15 points. So, this is a common paradigm used in machine learning. I get the indices numpy to random choice between 1 and 49. So, it will give me 15 numbers out of the range 1 to 49, replace equal to false, which means it will not repeat any numbers, and then I create a smaller subset of x total of idx and y total of idx, and I fit this models of various depth. So, now you are seeing that, let me show with 0, it will be easier to see with 0. Okay. The points which are shown with the blue border, can you see the points of the blue border? Yes. So, those are the points which have been randomly chosen for this particular model to be trained on. Right. You can see that these points are different for the different experiments that I have done. I am doing 10 iterations. In each iteration, I pick up a different random subset of 15 points. For example, this particular point in the second iteration is not present in this point, in this iteration. Right. So, if given the different iterations, I will learn different models on the training set given to me, right. So, for example, you can very clearly see that this orange line that you are learning is slightly below this orange line, right. Similarly, the different orange line are at different level. And this also happens with different degrees. So, this was degree 1, you can see that these lines are quite different. For degree 8, can you now see that the learned functions are very, very different from each other, right. Degree 0, they were all lines parallel to the x axis, and the values were deviating a little bit, but not too much. Here can you see the functions look very, very different. For example, if you look at this function, here for x equal to 0.5, it gives you a value of 1, whereas for this particular model, for x equal to 0.5, your value of y is minus 1. So, these models are quite different from each other. So, now let us do this exercise. I have to run. Does anyone have a sense of where we are going at? How is this related to overfitting and underfitting and the term bias and variance? If you get that idea, you have already cracked this concept. Okay. Now, I did those 10 different random subsets for a polynomial of degree 0, and I am showing you these 10 different models and the predictions. Right. I can now take an average of all of these, right, or the expectation of all of these, and assume that this is my learned model, because I could have been given any random subset of the training data set. It is just by chance that I had been given some, right. If I consider all the possible training data sets that I could have been given, maybe this is the blue line that you are seeing is my prediction. Okay. What do you think the green region is highlighting? The blue region shown here is my true function. The orange region which I am showing here is, I am calling it f hat. I am calling it as f hat, sorry, not hat, f bar. Bar is typically used in machine learning statistics literature to indicate what? The expectation of the mean, right? What is the expectation carried over or the mean taken over? The different models, the different estimators that I could have learned, right? So, if I look at, so you look at the 10 different black lines, they are f0, f1, f2, f3 till f10, f9, and I take the mean of all of them, which is shown here in the blue line, but here it's shown in orange, right? So, you look at the ground truth function and you look at my expected prediction from the function, right? And I am looking at the difference between these two. I am calling this to be my model's bias, right? How biased is my model, or how different is my model's prediction compared to the true function, right? So, this was a very simple model, depth 0. You can see that the green region highlighted is very large. So, what does this tell you? For low complexity models, the bias is high. If we increase the complexity, would you expect the bias to get low? Let us verify. Let me go from 0 to 1. Can you see that the area in the green region has decreased? Right? It is still some line that I have learned, but the area has decreased. I go to depth, not depth 2, complexity 2. Now, can you see that the bias is very low, right? And now, can you see that my model is unlikely to be underfitting? It is fitting well here, right? Whereas, with depth 0, my model was underfitting, right? My model was exhibiting a high bias, it was not able to capture the true function very well, right? And the bias is between the true function and my predictions. The difference between a predicted function or the average predicted function and my true function, that I am calling to be the bias. Typically, when quantifying bias, we never use bias, but we use bias square, because otherwise bias would just cancel out. Positive and negative would just cancel out. We typically use bias squared. For more complicated models, the bias is generally much smaller, right? So this is what we'd also seen earlier. As you increase the complexity of the model, the underfitting will reduce, right? The underfitting will reduce because you'll be able to give a more complicated model to fit on that data set. At the same time, from the bias perspective also, you can see that as a consequence, the bias or the gap between the true function and your function of interest will reduce. Right? As complexity or polynomial degree or depth in decision tree increases, bias reduces. But then something else increases. That's where overfitting occurs. What could that be? Variance. Variance of what?
Predicted.
Of our predictions coming in from the different functions. So let's view that also. So this is showing my variance coming in from the degree 0 function that I was learning at, right? This is basically showing the different lines that I learned, right? I'm just showing one standard deviation. If you were to show two standard deviation, this would look slightly broader. So basically what I'm showing is I'm looking at the variance amongst these different y values across these different functions that I've taken. For a degree 0 curve, degree 0 function, the variance is quite low, right? Can you see that the highlighted region is quite low? Whereas if I had chosen degree 1, it seems to be slightly more, right? Not huge, slightly more. This one seems to be just an anomaly. Now, slightly larger, even bigger, right? Can you see also that the function is now assuming much more complicated form, which earlier was not possible? Has the variance increased significantly now? Even more, right? Why is this behavior occurring? Why is the variance increasing as we're increasing the complexity of the model? So your model being more complex means it has more degrees of freedom. It means it has more tuning knobs. It means it can have more fine-grained control and fit the training data set well. But let's look at this. We're looking at a complexity of degree 8. Let's look at what we had. Right. So these are the different functions shown in orange, which we have learned for degree 8. Each of them is almost passing through the training data points, right? But the training data points we have passed is also different for each of them, right? Which means that in order to fit each of the training point well, which is a smaller subset of the larger data set which could have been made possible, you will see that it ends up learning very complicated functions, very different and complicated functions, because it has the complexity to do that, degrees of freedom to do that, whereas a simpler model doesn't have that capacity. Right? So as a consequence of that, if you were to just look at, I showed this example, right? If you just look at x equal to 0.5, the y values that you get are negative, 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 positive, negative, positive, positive, highly negative, somewhat negative, and so on, right? So for each point you see that you can have a huge variance in terms of negatives and positive values that you're getting. So therefore the variance, once you choose a very sophisticated model, increases a lot, right? And this is also the same meaning which we saw. If you make tiny perturbations to the training data set, your model changes a lot. Can you see that? Now I've made a tiny change. I've just moved 1 point from here to there, or 1 point which was earlier training point. I have now not used that or have used that. That makes a model highly different, which means that a model is exhibiting high variance. It's trying to adjust to the nuances, to the very specifics of the training data set which has been given to it. Therefore, it may not do a very good job at generalizing. So, thus, as the complexity increases, the bias reduces. As the complexity increases, the variance increases. Right? So, therefore, in machine learning, we are generally, or the bias squared instead of just the bias. Therefore, in machine learning, we are always trying to play the balancing act between underfitting and overfitting, or in other terms, the balancing act between bias and variance. We want to choose something in between those. And this next cell, I am plotting both the bias and the variance. So, typically the trend should follow, because again I am using a very toy data set. So, you may not always see that the bias is increasing and the variance is decreasing with complexity and the variance is increasing. Here you can see that broadly, as you increase the complexity, the variance is increasing, and broadly as you increase the complexity, the bias is reducing. There are some small things which are happening here, which are due to very small experiment that I have done. I have only looked at 10 iterations. I have only looked at a small number of samples. I have only looked at some specific models. But broadly, this is the trend you will see. Bias decreases as you increase the complexity, and variance increases as you decrease the complexity. So, if we have to just summarize today's lecture, we looked at decision trees case 4, which is real input, real output, where we looked at how to make a prediction. We said that we will sort the attribute in increasing order and choose split points by dividing into sub-regions. After that, we looked at the bias variance trade-off or the underfitting overfitting trade-off, where we said that let us look at the regions in which the model is not able to train on the training data well, underfitting or high bias, and the regions in which the model fits very well on the training data, but does a very poor job on the test data, which is overfitting or high variance. We will end today's lecture now. I will request if someone can please pass me the attendance. I just need to, I will randomly call out 5 people and I request them to please raise their hands. On Friday, we will have a coding session plus some other theory we will study. Okay, Nimit. Do we have Nimit? Okay. Do we have Aditya? Aditya Gupta. Do we have Nihar? Okay. Rushi. Hitesh. Jaiswal. Hitesh Jaiswal. Hitesh Jaiswal. Okay. Thank you. We'll meet on Friday.